This is the brief on thermal boundary conditions in heat transfer. All right, so we're diving into why boundary conditions are such a big deal for figuring out how heat actually moves. We're really going to focus on something called the Robin condition, because it's fantastic for modeling how things cool down in the real world. Okay, first up, the Robin boundary condition is basically just Newton's law of cooling in math form. All it's saying is that heat transfer, like from a hot engine, depends on the temperature difference. Heat always moves from the hot thing to the cold thing. Simple as that. Second, what makes this condition so powerful is that it looks at two things at once, the surface temperature and the temperature gradient. And that gradient, that's just a fancy term for how steep the heat drop is right at the boundary. So the heat flow depends on both how hot the material is and how fast that heat is trying to escape. Finally, the real magic here is that Robin gives you a realistic, middle-of-the-road result. Think about the two extremes. You've got the Dirichlet condition, which is like max cooling, maybe down to 20 degrees. Then you've got the Neumann condition, perfect insulation, so zero heat flow and the highest possible temperature, say 100 degrees. Robin models actual convection, like air cooling, and lands right in that sweet spot in the middle, giving you a sensible result, like 33 degrees. So really, understanding these three types shows you that the thermal state of an entire object is dictated by what's happening right at its edge.